All right, welcome. Today we're diving into a problem that's like fundamental to computer science. How do you put things in order? I know, it sounds super simple, right? But the search for the perfect way to sort things has led to some of the most clever, most ingenious ideas in all of programming.
So let's just jump right in with a huge question. Imagine you've got a million things. Could be anything. Songs on a playlist, customer records, you name it. And you've got to sort them right now. How do you do it? Well, the answer isn't just one magic bullet algorithm. It's actually a story. A story about making really smart trade-offs.
Okay, first things first, let's make sure we're all on the same page. When we say sorting, what do we mean? It's really just arranging stuff in a specific sequence. You know, numbers from smallest to largest, names in alphabetical order. And this simple little action, it's the hidden engine behind so much of what we do, from searching a massive database to even rendering graphics in a video game.
So to figure out which sort is the best, we can't just go with the gut feeling. It's not that simple. We need a consistent way to measure them, kind of like rules for a competition, right? So how do we judge a sort? What are the rules of the game?
Well, we basically judge them on three key things. First up is time complexity. And all that means is, how much slower does this thing get when you throw more and more stuff at it? Then you've got space complexity. How much extra memory does it need to get the job done? This is a huge deal for, say, your phone, which has limited memory. And finally, stability. This one's a little subtle, but super important. If two items are technically equal, like two people with the same last name, does the sort keep them in their original order? You can imagine why that's critical if you want to sort by last name, then by first name. Okay, with those rules in our back pocket, let's check out our first batch of algorithms. These are the kinds of sorts that you'd probably invent on your own if I just handed you a shuffled deck of cards. They're super intuitive, makes total sense. But as we're about to see, that beautiful simplicity, it comes with a price.
And we're going to start with an absolute classic, bubble sort. Ah, yes. This is the one pretty much everyone learns first in computer science class. And here's the funny thing. It's not because it's good. It's because it's a fantastic way to learn.
The logic here is, well, it's about as straightforward as it gets. You just walk down the list, one step at a time, and you compare an item to the one right next to it. Are they in the wrong order? Swap them. That's it. You just do that over and over and over again. And with every full pass, the biggest unsorted item bubbles up to its final spot at the end of the list. Couldn't be simpler, right? But, and this is a huge but, here's the catch. For a totally random, jumbled up list, bubble sort's performance is what we call n squared, or n squared. Now, n is just the number of items you have, and n squared means for every single item, you might have to look at every other item. So if you double your list from 10 items to 20, the work doesn't double, it quadruples. It gets slow really fast. The only time it's even remotely okay is if the list is already almost sorted to begin with.
Yeah, and another one of these intuitive sorts is insertion sort. This quote absolutely nails it. It's just like sorting a hand of playing cards. You build up your sorted section one card or one item at a time. You just grab the next unsorted item, look through the part you've already sorted, and slide it into the right place. It's a way better approach than bubble sort, especially for smaller lists.
So these intuitive sorts, they're fine for small jobs, but throw a massive data set at them and they just hit a brick wall. This is where we get the real breakthrough in the history of sorting. It's a completely new way of thinking, a powerful strategy called divide and conquer.
And the idea behind it is just so elegant. Instead of trying to wrestle with this one giant, messy problem, why not just break it into a bunch of smaller, more manageable pieces? You solve those little tiny problems, which is way easier, and then you just very cleverly put all the solved pieces back together. Seriously, this approach was a total game changer for sorting huge amounts of data.
And this strategy brings us to the two heavyweights of the sorting world, merge sort and quick sort. On average, they are both wicked fast. They run in what's called O(n log n) time. Now, if n squared was like a slow, painful grind, n log n is, well, it's way, way smarter. Think about finding a name in a phone book. You don't read every single name, right? No, you open it to the middle, and you keep splitting the problem in half. It is a massive leap in efficiency. But here's the thing. These two represent a classic trade-off. Merge sort is your reliable workhorse. It guarantees that fast performance, but it needs extra memory to do its thing. Quick sort, on the other hand, is usually even faster and uses less memory. But it has this rare, worst-case scenario where it can suddenly slow way down. So it's a choice. Do you want reliability or do you want raw speed?
Okay, so all the algorithms we've looked at so far work by comparing items. Is A bigger than B? Is C smaller than D? But what if you already know something special about the data you're sorting? See, sometimes the fastest way to get something done isn't with a general all-purpose tool. Sometimes you need a specialist. The right tool for the right job.
So let's meet one of these specialists. It's called counting sort, and it has a totally different way of thinking. It's a non-comparison sort, which means it doesn't bother asking, is this bigger than that? Instead, it just counts. It looks at the whole list and just asks, okay, how many ones are there? How many twos? How many threes?
Now here's the deal. Counting sort has a superpower, but also a kryptonite. Its superpower is that it's lightning fast. We call this linear time. But its weakness, its kryptonite, is that it only works if the range of numbers you're sorting isn't massive. So it's absolutely perfect for sorting, say, 1,000,000 test scores that are all between 0 and 100. But it would be a complete disaster for sorting 1,000,000 phone numbers, because the range of possible numbers is just gigantic.
Okay, we've seen the simple stuff, the powerful divide and conquer methods, and the super-focused specialists. But what's the big winner? What algorithm is actually running behind the scenes, sorting your photo library or your contact list right now? Well, it turns out that champion of the modern world isn't one of these. It's a really clever hybrid that just steals the best ideas from everything we've just talked about.
Everybody, meet TimSort. This is the algorithm that's the default in languages like Python and Java, and honestly, it's brilliant. It was built on one simple but genius observation. Most data in the real world isn't totally random. It usually has little pockets of stuff that are already sorted. TimSort calls these runs. So what it does is, it zips through the data, finds these natural runs, and then uses the raw power of merge sort to combine them. And for any small, messy bits, it just uses the quick and nimble insertion sort to clean them up.
Yeah, this visual is a great way to think about it. TimSort is just a pragmatist. It's smart. It uses the right tool for the right job at every single step of the way. It uses the quickness of insertion sort for all the small, easy tasks, and then it pulls out the big guns, merge sort, to do all the heavy lifting of combining everything. It really is the best of both worlds, all rolled into one.
So, what's the big takeaway from all of this? I think it's this. There's no such thing as one perfect sorting algorithm. It just doesn't exist. There's only the best algorithm for a very specific situation with its own data and its own limitations. The art of creating order is really the art of making smart trade-offs. So the next time your app or your phone sorts a list instantly in the blink of an eye, just stop for a second and think about it. Which trade-offs between speed, memory, and stability were just made for you?